Okay, guys, so what we're going to start today is the next section in the new unit. So it's going to be from 8.3 on series of terms. Okay, so we're probably going to spend a couple days on this section, so I'll go ahead and designate this as a day. One thing to recall, since you just had your test earlier, is we've been looking a lot recently at sequences. If you remember, a sequence is basically just a list of numbers. Okay, we have to give them in a particular order, so if I change up the order of what's in my sequence, 1, 2, 3, 4, 5, 6, 7, 8, 9 versus 2, 1, 3, 4, 5, 6, 7, 8, 9. Okay, we've got different sequences. What's new today are these things called series, and not too much of an extension. Here, a series, this guy is going to be the sum of a list of numbers. Okay? Now, we've looked at sums before, way back in Calculus 1. You guys used something called sigma notation sometimes to denote how we added up pieces for Riemann sums. And how it worked was this. Okay? To compute my sum of a list of numbers, we'll write out something that looks a little bit like this guy. Okay? Here, I've got my sum from k equals 1 to infinity, okay, of my sequence a sub k. Now, before we used a sub n to denote my sequences, the indexing variable really actually isn't terribly important. If you use n, if you use k, if you use p or r, it doesn't really matter. Here's how the pieces break down in this. Right? First off, this big capital sigma tells me we have a sum. So we're adding a bunch of stuff up. Then there's all these other three pieces, right? The k equals 1, this is going to tell me my variable and my start number. My a sub k tells me my formula for the stuff I'm adding. My infinity up top, when we were doing Riemann sums, this would be a finite number because it would tell us where to stop. Since we're adding up a sequence, and these are usually infinitely long, this means we have an infinite number of things to add. We're not really going to stop adding. Okay, so this guy is going to tell me what my stop number is. Okay, so once I break all of that down for this particular series that I've written out, since we're going from k equals 1 to infinity, that means that when I look at this formula, I'm going to add up everything starting with my first term, k equals 1, and then I'm just going to keep going until I hit my stop number, okay, which is going to be never because it's infinity. So in this particular case, this is shorthand. Oops, should be a plus sign here. A sub 1 plus a sub 2 plus a sub 3 plus a sub 4 plus, okay, dot, dot, dot. You guys get the point. We keep going here. All right? So I'll go ahead and give a fast example of how we might do this notation here. Let me go ahead and actually move this all the way out. As an example, say I want to take my sum of a list of squares, and we'll go ahead and start at, let's say 4. Okay, so if I want, 16 plus 25 plus 36 plus 49 plus 64 plus so on and so forth, you guys hopefully see the pattern. This is 4 squared plus 5 squared plus 6 squared plus, okay, we're going to keep going. We're adding up squares of integers. Another way to do the shorthand for this, so I don't have to write as much stuff all the time, is going to be to use my sigma notation. Okay, now you notice everything is in the form something squared. So the thing that we're summing looks like k squared. The number that we started on was 16, so the first thing that we plugged in to get that was 4. This means we start at 4, and we keep going since this guy is an infinitely long list of terms. Okay? Now, as far as how to actually compute this thing out, how do I add these? Okay, because, in this particular case, sure, this blows up, but we've seen before, like for example, when we were talking about my improper integrals, and we did that thing where we split my boxes over and over and over again, sometimes we can add infinitely long lists of numbers and get back things that are totally finite. So we're going to compute these with something that's called partial sums. What we want to do is find my sequence of partial sums. Well, I guess I'll go ahead and write this in here. My sequence of partial sums. So to go ahead and define this, the sequence of partial sums of a given sum, okay, my sum from k equals 1 to infinity, a sub k, this is given by the following. We're going to denote this a new sequence, and I'm going to give this in equation notation. Okay, we'll call this new sequence S for sum. And how I'm going to find it is I'll take a sum of my list of terms that I'm adding up, and I will start at whatever I initially started at, but I'm going to stop at n. Okay, so if I write this out, this is basically a1 plus a2 plus a3 plus you're going to keep going until you hit the nth term, and then you stop there because that was our stop number. Okay, so if I'm taking this sequence of partial sums, this is why we call it, okay, a sequence, because if n changes, if my stop number changes, I'm going to get a new list of terms. I'm going to call this partial sums because what we're doing is we're not adding up the whole thing over here. We're adding up the first term, and then the first 2 terms, and then the first 3 terms, and then the first 4 terms, and we kind of keep going. Okay, so I'll give you guys an example here. First off, again, to highlight, for S1, this is A1. For S2, you add the first 2 terms. For S3, you add the first 3 terms, A2 plus A3. Okay, and then we keep going here. Okay, so let's try that example that we did when we were looking at improper integrals. All right, so I'll consider my sequence 1 over 2 to the n added up. Okay, so my series for 1 over 2 to the n. Okay, n equals 1 to infinity. So just kind of a refresher here, what I'm referring to, this was that situation where we had this unit box, and we cut it in half, and we cut it in half, and we cut it in half. Okay, we should expect that if you add a half plus a fourth plus an eighth plus a 16th, which is exactly what we're doing here, we expect my sum to give me 1, right? Because I added up all these fractions, and it should give me my whole unit box back. Okay, so let's look at the sequence of partial sums. Here, S1 is going to be my first term, so I plug in 1 because my start number is 1, and I get a half. S2 is going to be my first 2 terms, so my first term is a half, my second term is 1 over 2 squared, that's a fourth. We can kind of keep going here. S3 is a half plus a fourth plus an eighth. S4, this guy is a half plus a fourth plus an eighth plus to the 4 in the denominator. This is going to be 1 over 16. And we can kind of keep going here, right? If I keep filling these guys out I'll get my pattern. Now, right now it's not really obvious that these are going to add up to 1, so let's see if maybe we can introduce a common denominator here. In this particular case, well, this guy's giving me a half. I don't have to change much there. I'll kind of shortcut this and let you guys verify what's going on later. You can work this out by hand if you want, but we're in a video. You guys can pause it and double check my work if you want. My common denominator here is 4. This is 2/4 plus 1/4, so I get 3/4. My common denominator here is 8. This is an 1/8 plus 2/8 plus 4/8, so I get 7/8. My common denominator here is a 16th, so I get a 16th plus 2/16 plus 4 of them plus 8 of them, and this is going to give me 15/16. So one thing to kind of notice is what's happening is if I'm looking for a pattern to try and describe this sequence, we've got 2, 4, 8, 16 in the denominator. Okay, so we've got powers of 2. And we've got a number less than that in the numerator. Okay, so 1 is 1 less than 2, this is 1 less than 4, this is 1 less than 8. So if I'm trying to generate some sort of pattern here, okay, to kind of fill in my blanks, my general sequence, Sn, and a lot of your last section was looking at, patterns like this and trying to come up with a formula. Okay, we've basically got 1/2 plus a bunch of junk all the way out until we stop on this nth term. And my general pattern here is I'm stealing whatever the heck this last denominator was. Okay, so since this is S4, that was me plugging 4 into this guy. Okay, here this is S3, this is me plugging 3 into this guy. I'm basically taking 2 to the n, okay, and plugging this number into it. Okay, so my denominator gets swiped from my very last term. And then, like we said before, subtract 1 up top. And if I'm looking to figure out what my sequence of partial sums does, okay, the limit of the sequence of partial sums gives the limit of the series. Okay, so if you can figure out a formula for Sn and then take a limit of it, you know what it adds up to. In this particular case, if I'm taking a limit of this guy, this is going to blow up and this is going to blow up. I hit this with L'Hopital's rule and the 1's going to drop off and I'll have the same derivative on the top and bottom. So in a case like this, here my series adds to 1. Okay? And my reasoning for that, if I want to know why my series adds to 1, again, it's because my limit of my sequence of partial sums, so my limit of this thing, goes to 1. Alright? See if we can maybe take a look at a different kind of example. This is a special kind of example called a telescoping series. Okay, and you'll see a couple of these guys. We'll talk about why they call it telescoping. Okay, suppose I look at something like my series where I am summing up terms from 0 to infinity, and my formula that I'm using here is 1 over k plus 1 minus 1 over k plus 2. Okay, so in a case like this, again, we want to write this out and figure out what my general pattern is here. So I'll go ahead and start with, we'll kind of change my convention slightly. We'll just start with whatever my indexing term is here. So we'll get an S0 when I start with my 0th term, which is 1 minus a half. For S1, I want to add this 0th term. Oops, there should be a minus. My 0th term plus my first term, which is a half minus a third. For my S2, I want to add my 0th term plus my first term plus my second term. Okay, and hopefully we kind of pick up on the pattern that's going to be happening here. Notice if I've got my nth term in my sequence, okay, I'm still adding all of this junk up, but I'm basically going to keep going until I hit my nth term, which you plug n in up here. So it's going to be 1 over k plus 1 minus 1 over k plus 2. Now, kind of like before, just looking at this outright as is maybe doesn't give you a lot of hints on where the sequence is going, but what we can go ahead and do is, simplify like we did before. Last time we found a common denominator, we added everything up. Here what we're going to do is note cancellations. All right, there's nothing to cancel really up here. We could simplify it and just get a half, but we're going to pause on actually summing things up so we can try and notice the pattern a little bit better. If you pay close attention here, you'll see that on this first pass, we're canceling these halves because this one's negative and this one's positive. On this next pass, we're canceling the halves again, okay, and we're actually going to do that down here too. But we also have thirds to cancel. And again, we'll do that on this last one too. You should notice that once we keep adding these terms, anytime I tack on a new term, here my next piece that I left off for my dot 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 would have been a fourth minus a fifth. Anytime I add on a new term, the pattern is that all my inner things cancel out. So in this particular case, I'm going to have a 1/4 minus a fifth term, so this is going to cancel. Over here, I'm probably going to have a 1 over k minus 1 over k plus 1 term, so this guy's going to cancel. So if I'm looking at my general pattern here, again, for each of these, this is looking like 1 minus a half, simplify it if you want. This is looking like 1 minus a third, simplify it if you want. This is looking like 1 minus a fourth, simplify it if you want. And this guy, after all of my cancellations, oops, these should be n's, not k's, sorry about that. After all my cancellations, here, we're left with just a 1 over n plus 2. Okay, so 1 minus 1 over n plus 2, simplify it if you want. Okay, now recall we said that my limit of Sn is equal to my sum of my series. Well, here my limit as n goes to infinity of Sn. This is really my limit as n goes to infinity, 1 minus 1 over n plus 2. So this is also another one of these series that adds up to 1, because here my denominator blows up, means that fraction gets small. We're just going to be left with the 1 there. Okay, and the reason that we call this telescoping is if you've ever seen, one of those old-timey stranded at sea kind of, they've got a telescope to look out on the horizon, and it's this thing that stretches outward, and you could kind of adjust it. This is what they're kind of calling telescoping here, because you can stretch this out and then pull it back to cancel, and then we're stretching it back out and we're pulling it back to cancel. So this is kind of getting bigger, smaller, bigger, smaller, bigger, smaller, or vice versa, smaller, bigger, smaller, bigger, smaller, bigger, as we continue and make all of our cancellations out. Okay, so if you see a minus sign in the middle of something like this and you're trying to figure out, what is my limit, chances are it might be one of these telescoping things where you have to observe some cancellations. And again, this is all pattern recognition. Don't just always assume that the middle pieces are always going to go. Watch out for which piece cancels with which piece. Sometimes if these aren't offset by just one unit, your cancellations might be a couple spaces apart. Okay? So, try another example here. Here we can kind of a little bit more concretely see what happens when we sum up some sequences that we've looked at before. Oops, I'll go ahead and make these guys K's like we've been using. This is that alternating sequence. Minus 1, 0, we'll start at 1. Minus 1, 0, minus 1, 0, minus 1, 0. So I can go ahead and add this all up and get that if I start at 1, my first term is minus 1. And again, we're alternating. So this is minus 1 plus 1. Whereas 3, this is minus 1 plus 1 minus 1. Okay, and hopefully you guys can, again, see this alternating pattern. If I go to sum this up, we start out with minus 1. Here, these guys cancel and I get 0. Here, my cancellations, minus 1, 1 gives me minus 1. Here I've got two sets of cancellations, so I got 0. Probably the simple pattern to pick out here is that I've got that Sn is going to be, well, on all the odd terms, it comes out to minus 1, if n is odd. And this is going to come out to 0, okay, on all these even terms, if n is even. So this sequence is basically minus 1, 0, minus 1, 0, etc., and it alternates just like the original one does. So here, if I want to look at the fact that Sn diverges, okay, this diverges very much for the same reason that the sequence we're adding up diverges in the first place. We're never honing in on a particular number. We're always balancing back and forth between two numbers for forever. Okay, so since we never close in on a single thing, this guy diverges. That means my sum from k equals 1 to infinity of minus 1 to the k, this guy diverges too. This doesn't add up to anything. We were kind of lucky in the previous two cases. You know, we add up this infinite list of numbers and we get something finite back. Like you might expect, that doesn't always converge to something. Okay, so my guess is this guy doesn't converge at all. And, you know, we can go ahead and do kind of another intuitive, more intuitive one here. Suppose that I take a sum from 1 to infinity of k. Well, let's use some common sense here. K is just that counting sequence, right? So S1 is 1, S2 is me adding the first two numbers, S3 is me adding the first three numbers, etc. I'm not even really going to pick out the pattern here. You guys know that the counting numbers themselves blow up. So if I'm adding all of the counting numbers, this is going to blow up too. Okay, so you know, some of these are a little bit clearer than others. This should pretty obviously diverge. Okay, because heck, the n terms that we're adding get really, really big here. Okay, so this guy, that's not going to converge at all. So my sum isn't going to converge here either. All right, now I kind of want to change gears a little bit here. We've been talking about how to add up these infinite lists of numbers directly. I'll give you all a hint. You're not always going to want to do this directly because that's probably going to be a pain in the butt. So we're going to look for a couple shortcut tricks that'll make it a little bit easier for us to maybe save or repeat some of the work that we've done before without having to do everything from scratch all the time. Okay, so there are a couple algebraic rules for adding my series here. Okay, and the first one is on addition. Okay, if I've got two series, say I've got a sub k that I'm adding, and you know, let's say that comes out to some number, I'll call this capital A, once I've added everything. And if I've got another series, let's say I call this guy B sub k, so this adds up to some sort of finite number. Okay, if these guys both converge, okay, then I'm going to get that if I take my sum of my sequences here, I don't have to consider this as one big chunk. I can split it into pieces. So series, in a way, they're a little bit like integrals, which makes sense because, integrals came from series, these Riemann sums. Just like integrals, you guys can split these apart if you know you're getting finite things back or convergent things back for each piece. So ultimately, I can just add what happens together. Now, as an example of this, we just figured out what the heck happens if I take 1 over k plus 1 and subtract off 1 over k plus 2. We also just figured out, not only if I add this here, actually I'll kind of shift this a little bit so this is kind of cleaner. You'll notice, and I'll go ahead and bring the example back momentarily here. We started the indexing at this guy at 0, so that my first term was 1, and then my next term is minus a half, and that changes ever so slightly. We'll make it so the first term is 1 that we have, and the first term we're subtracting off is minus a half. So this is slightly indexed differently from how we wrote it before, but it's going to give you the same exact sequence. Okay, 1 over k minus 1 over k plus 1. We've looked at something very, very, very similar, and we've shown that this piece adds up to 1. We've also looked at 1 over 2 to the n, which here I don't have to fudge the indices to make it match up. All right, so I know that this piece, this initial piece, this converges. It adds up to 1. This piece, this guy converges. He adds up to 1. If I know that both of those pieces are finite, I can split them apart. So I've got my two series together here. And I know that this comes out to 1 and this comes out to 1. So all in all, rather than having to write out S1 is 1 minus a half that plus what happens when I plug in 2, I don't have to do this from scratch again. I already did the work. I'm going to be lazy and look at my old work, and we can save ourselves a lot of time and not have to do this all over from scratch. Okay? So there's that. As far as other theorems, okay, we also get a couple other theorems that are pretty similar for, I said like integrals, we can split my series apart if things converge. You also have a similar notion of being able to pull constants out, right? If I have a series that converges, and let's say that alpha here is any real number, then I've got the following, okay? If I've got alpha times a sub k, this is going to be the same thing as if I pull that alpha out. So if I know that this guy converges, I presumably might know what to, and then I can actually just compute this without having to write that stupid alpha in every time. Okay, so my idea is this is basically a distributive property if we really think about it. Here, this first piece, if I actually, write out term by term by term what I'm summing, this looks like alpha times a1 plus alpha times a2 plus alpha times a3 plus so on and so forth for forever. Well, if every single term has got an alpha stuck to it, distributive property is going to let me pull this out. And really, that's what it looks like when I write out this side. Right? This is alpha times this big long sum. So here's what we've got to thank for this. We've got distributive property, okay, to help us simplify there. So kind of an example, say that I've got something like, 5 over 2 to the k that I'm summing from 1 to infinity. 5 is a constant I can go ahead and pull out. So rather than sitting out and writing my sequence of partial sums and trying to figure out the pattern when I've got this stupid 5 on top, I can look at this and say, oh, this is something that I've already done. We know this piece adds to 1. Okay, so this comes out to 5. And notice we didn't have to sit here and pattern recognize again with a new function. Just turn it into something that we had already seen before to kind of simplify this. Okay? Some other comments, because we did a couple of examples here where we found stuff and it converged, and we did a couple examples where we threw stuff together and it didn't converge. What I want to give you guys is a bit of a time saver so that, why go through all of this trouble and pain and work to try and figure out what something adds up to if, in the end you note all your cancellations mess up and this guy actually blows up or doesn't go anywhere, okay? Is there a shortcut for how we can figure out whether or not we converge or diverge so that we don't have to do all of this? Well, there's a number of shortcuts. There's a number of tests for figuring out whether you converge or diverge. I will start out and give you guys a theorem, okay, the first of these shortcuts. This is called my divergence theorem. This will help me evaluate these because it will help me rule out ones that I don't need to add because I know they don't go anywhere. What this says is that if my sequence that I'm summing does not go to 0 as k goes to infinity, then when I go to add everything up, my series diverges. Here's the intuition behind this. If your sequence isn't shrinking off really, really, really tiny towards the end of it, that means that when you're adding stuff towards the end of this, you're not closing in on a number, because if you're not having these really small end terms, if you have a really big end terms, the end of the sum is going to be bouncing around a lot. If the end of the sum is bouncing around a lot, it's not going to go anywhere. So some examples that we've already noted. Okay, this minus 1 to the k, this was a sequence that doesn't converge, so the series didn't converge. Okay, another one that I looked at, this was more of a common sense one that we argued. If I'm adding up k, so 1 plus 2 plus 3 plus 4 for forever, obviously k doesn't go to 0, so the tail end of the sequence isn't going to close in on anything. This guy's going to diverge too. Okay, my sequences did not go to 0, so my series both diverge. Okay, and I'll give you guys a little bit of warning here. If I know that my sequence, okay, so not the sum of the list of terms, just the list itself, if I know my sequence doesn't go to 0, this means that this guy is going to blow up. You don't necessarily get the converse statement. And what I mean by the converse statement is if your sequence goes to 0, this doesn't mean convergence. Okay, so I'll go ahead and write this as a cautionary note. A sub k going to 0 doesn't always mean convergence. Okay, but it is necessary for it to happen. In other words, for example, my 1 over k minus 1 over k plus 1, or the alternate version, 1 over k plus 1 minus 1 over k plus 2. This guy goes to 0, and we saw that the associated series converged. But here's kind of a weird example. This is called the harmonic series, right? My harmonic series, this is actually something that diverges despite, or I guess my sum diverges, so I'll be specific here. My series diverges despite my sequence shrinking. Okay? This guy is when I add up everything of the form 1 over n. So this will be like 1 plus a half plus a third plus a fourth plus a fifth plus a sixth, so on and so forth. I'll go ahead and write this out. 1 plus a half plus a third plus a fourth plus a fifth plus a sixth plus a seventh plus an eighth plus, hopefully we'll get the pattern here. And here's why. Okay? Here's kind of the idea. It's not clear whether or not this converges or diverges right now, but I am going to group this up and see if we can notice some sort of a pattern. Okay, I'm going to group it up in this manner. My 1, my 1/2, I will take the next 2 terms, I will take the next 4 terms, and I will take the next, we'll kind of fill this in here, I will take the next 8 terms, and this is actually going to go all the way to 1/16. Right? So hopefully we see the pattern. We're ending on all these powers of 2 in my denominator. Now, if I do that, here's what happens. Okay? This collection that I've added, this is actually going to be bigger than the following. Okay? Now, 1, this is the same as 1. That's fine. A half, this is the same as a half, this is fine. This is where I'm going to actually do my inequality, okay? Notice that whenever you make your denominator smaller, you shrink your fraction. So I'm going to make some of my denominators smaller, okay? If I make the 3 into a 4, we've now justified our inequality, okay, because this is bigger than this guy. Similar deal over here. If I make all of these numbers smaller, so if I make these a bunch of a's, this is smaller than above. Okay, up here, if I make these a bunch of 16ths, this is smaller than above. Now I'm going to kind of clean this up. Okay, this really looks like 1 plus a half plus this is a half plus this guy is also a half because there's 4 a's plus this guy is also a half because there's going to be 8/16. Okay, notice we're adding the string of halves for forever. That guy diverges to infinity. Okay? So, what I'm going to go ahead and do with that in mind, okay, this demonstrates my sequence goes to 0, but my series does not. Okay? So, there's a distinction here. 1 over n goes to 0, but when you add everything up, okay, when you add everything up, this goes to infinity. What I'll do right now is go ahead and give you guys that quiz that I mentioned. What I want you all to do is try to find a sequence of partial sums for me. Okay, and the series that we'll look at will be this one. It'll look very close to that telescoping one we did before. Here, we'll start off with 1 over k. I'm going to jump a couple terms down, though. So we'll look at 1 over k plus 3. So what I want you guys to do is write out the first few of these, 2, 3, 4, however many of them that it takes for you guys to figure out the pattern. Okay, tell me what SN is. And then tell me what this converges to. And I will give you the hint here, it does actually converge. Okay? So if you've got questions, I'll try to keep an eye on my email. Otherwise, I'm expecting this back from you guys on Monday.